Okay, good morning. In the previous lectures, we have been discussing about interface advection techniques. Now, other than interface advection, whenever we are using the one fluid formulation for resolving multi-phase flow problems, there is one more important parameter. Okay, we know that in the momentum equation of one fluid formulation, we have majority of the terms identical to that of single phase flow, that is del rho v vector by del t plus divergence of rho v vector and minus gradient of p plus mu times uh, divergence v plus divergence v transpose, and then ultimately we have, this is the equation which is identical to that of single phase flow. Okay, other than this, what we have other than this, because we are resolving both the fluids using the one fluid formulation, so we have to also account for the force which is acting at the interface. So at the interface, the force which acts is surface tension force, which we typically call as F sigma on per unit volume basis. And this entire equation, you know that all the terms in this equation are actually on per unit volume basis. And whenever I will be solving this equation using the finite volume method, I will be integrating this equation over the different control volumes, and I will be doing its volumetric integral. Okay, but one important feature of this surface tension force is that it only acts at the interface between the two fluids. Okay, so typically if I take any two-dimensional grid, so even though I have added F sigma as volumetric term, and it will be used in discretization like F sigma into integral of dV, but ultimately if my only these cells are occupying the interface, then surface tension force should only be accounted for in these cells. The surface tension force should not go to other cells of the this grid. Okay, because there it will not be acting. So whenever we are selecting F sigma, we have to use its formulation in such a way so that this particular feature of surface tension force is actually implemented in the numerical solver. Okay, so how we can implement this? I can simply say that F sigma will be equal to sigma times, because it's a line force or a surface force, so depending upon the interface, so I can write it sigma times mean curvature of the interface. So kappa is actually mean curvature of interface. Is this point clear? That is my surface tension force. Now, because this force should be calculated only for the cells which are containing interface, so we have to multiply certain parameters which vanishes at all the cells which are away from the interface. So for that purpose, we over here take the gradient of color function, because the value of color function in all these cells will be 0 0. So that's why gradient will be in between this cell to this cell, this cell to this cell. Whenever I will be defining gradient at the edges of the cells, it will be 0. Similarly, where I am having 1 1, there also gradient will be 0. So gradient will be non-zero only at the cells containing the interface. So that's why if I multiply this with the gradient, then though I am adding surface tension force as a volumetric quantity in my mathematical formulation, but in that one term I have included which will be non-zero only at the interface. Is this one clear? So this takes care of the estimation of surface tension even in a volumetric equation at the interface. Okay, now whenever we need to calculate the surface tension, so sigma is something which is surface tension coefficient. Okay, and this surface tension coefficient is known for the fluid pairs which we are considering in our analysis. Okay, then second quantity is curvature. So kappa is mean curvature of the interface. So mean curvature of the interface is one important parameter which we need to calculate. And second point is we are also having gradient of C. So this gradient of C also we need to calculate. Okay, so gradient of C, we all know that if we know the value of C in different cells, then I can easily estimate the value for gradient of C. But ultimately, for calculating kappa, I do not have anything other than the value of C, because value of C is the only parameter which specifies the presence of interface. Okay, so typically you know that by using the value of C we can do interface reconstruction, and while we do interface reconstruction we can calculate the normal vector to the interface. So the information of normal vector to the interface can be employed for estimation of mean principal curvature. Okay, but this, whatever I am telling, everything we have to do it on a discrete arrangement. Discrete arrangement, because whenever we do the numerical simulations, we are not having continuous variation of the property. We consider that data is known only at the node points. So we have data available in the node points. So we have to solve this using the either finite difference method or finite volume method, any of the discretization method, but in a discrete manner. Okay, so let's try to see what are the different ways with the help of which we can actually calculate the surface tension force. So typically the computation of surface tension force can be separately done for interface reconstruction methods and front tracking methods. So one category we know that interface reconstruction, and second category is front tracking. So the methods which are used in these two category of methods are actually different. So you know that what is interface reconstruction? In case of interface reconstruction, depending upon color function, first we calculate the normal and then we place some piecewise linear lines in our grids to define the interface. And then we have certain advection schemes for advecting or advancing these lines with space and time. Okay. Second method, which I told you in the initial times, we did not discuss this method in detail, but I mentioned you that other way of tracking the interface could be that we will be putting some marker particles on the interfaces and we will be translating these using the Lagrangian formulation, and then by joining the path of these particles we will be getting the interface. So whether I go for front tracking method or if I go for interface reconstruction method, the method for calculation of surface tension will be different. Again, because I am not talking about front tracking methods in detail, majorly we are focusing on interface reconstruction techniques. So here I will be only explaining you the methods for estimation of surface tension which are used in interface reconstruction based techniques. These methods are CSF and CSS. Okay, so continuous surface force and continuous surface stress method. So let's first talk about continuous surface force method. Okay, so we know that F sigma has to only act at the interface. That's why I can write it in terms of sigma k, which is the force, and then I am multiplying it with delta S into N, which is actually equal to minus of gradient of the delta S into N is the Kronecker delta operator, which will be say 1 at interface and 0 everywhere. So this I can easily represent in terms of minus of gradient of the color function or height function, which I have written over here. Is this point clear? Now typically for height function we can use different type of formulations, and one of the important formulation which we typically use that is actually color function based approach. Okay, so if now what I need to do, because I am trying to calculate the surface tension in a discrete manner. So if I am trying to calculate in a discrete manner, I need to define it in terms of indices I and j, because whenever we have to go for numerical implementation, that we can do only in form of I and j. So let me consider this is row j plus 1 and j minus 1. This is I plus 1 and I minus 1. Okay, so let us consider that I am pointing or I am trying to calculate the surface tension force for a cell I comma j. So f of I comma j will be equal to sigma. Sigma is a constant quantity, it will be as an input parameter, okay, for a particular fluid pair, and then I am writing kh. Here subscript h denotes the numerical discretization. Okay, this H subscript is actually referring to numerical discretization. This point is clear because we know that the formula for curvature can be simply written in terms of divergence of the normal vector. Okay, curvature is nothing but divergence of the normal vector. Now, divergence of normal vector will be del nx by del x plus del ny by ny for a two-dimensional system. Okay, so del by del x and del by del y are the partial differential operators. Computers does not understand these partial differential operators. So we have to devise some ways to convert these partial differential operators into the subsequent discretized form. Okay, so that's why whenever I am referring over H here, it means that the curvature I need to calculate numerically. Is this point clear? Then second point is I am having this divergence of gradient of color function, and of course this divergence operator also I need to calculate numerically. Okay, and then I will be having normal vector which is also calculated numerically. Now we already know that normal to the interface can be given in terms of gradient of color function divided by magnitude of the gradient of color function. Okay, all of us know about this quantity. So normal can be computed using this way. So if I substitute this definition of normal vector over here, what will be happening? The magnitude of gradient of C will be cancelling out in the denominator and the numerator, and finally I will be getting f at I comma j equal to minus of sigma kh into gradient of C. Is this point clear? All are clear with this idea? So it means now my overall purpose is to calculate numerical discretization for kh and numerical discretization for delta h. Is this point clear? All are clear with this point? So these are the two things which I need to numerically calculate if I have to apply this particular formulation of surface tension force. Now let's try to understand this situation for a stationary fluid particle. Now consider that I am having either a drop or bubble which can be given as fluid 1 and outside is fluid 2. And this bubble or drop is just stationary present in any of the fluid medium. Okay. So if you recall earlier, I have told you that whenever we are having the stationary fluid particle, then in our momentum equation, we will not be having any temporal term because it is not accelerating. So temporal acceleration will be 0. Similarly, convective acceleration will be 0. Okay. Then viscous force why it comes? It comes purely because of the shear forces. Okay, so there for viscous force to act, the gradient of the velocity field should exist. So as it is stationary, no gradient is there, then ultimately my viscous force will also be 0. Now, if you take any physical scenario of drop or bubble present in surrounding fluid, then if it's a drop, you will be finding it will be falling in downward direction. If it's a bubble, it will be rising in upward direction. In order to make them completely stationary, we have to remove gravity term from our modeling approach. Okay, so because the situation I am giving you is a drop or bubble which is just of spherical shape and it is present stationary. Okay, to make it stationary, we have to actually remove the effect of gravity. Otherwise, it will be either rising or falling, and all my previous assumption will not be working. Okay, so that's why body force is also neglected. Now, what are the forces remaining? The forces remaining are only the pressure force, which can be because of curvature, and other is surface tension force, which will be acting at the interface. So my momentum equation for this type of situation will be only minus gradient of P plus F sigma into delta S equal to 0. All are clear with this point? Now this equation, when I will be numerically discretizing, I will be writing minus On gradient I have applied the numerical discretization operator H P minus sigma. One important thing, why I am trying to explain you this case first, because for the complex interfaces we need to calculate curvature numerically, but for this simplified situation, if it is not traveling and it is stationary and spherical, in that scenario the mean principal curvature will be already known to us. Okay, is this point clear? Because radius of a spherical bubble is fixed in both the principal directions. If radius is fixed, then its mean principal curvature will be simply equal to 2 by r. All are clear with this point? So that is fixed. So that's why when I am doing the substitution for surface tension force, I am writing it as K naught. I need not to calculate it numerically. It is simply a known parameter to me. All are clear with this point? Anyone is having any doubt? Okay. Now, this is a known parameter to me. If this is known, then what I need to calculate now? Gradient of color function. That I need to calculate, and this has to be equal to 0. Okay. Now, how can I calculate the value of gradient of P? Simply, if I have to calculate gradient of P at this phase between cells I comma j and I plus 1 comma j, this common phase is there, which is I plus 1 by 2 comma j. How I can calculate gradient? It will be simple, minus of, because minus sign is already there, P at time I plus 1 comma j minus Pij divided by delta x, which is a central difference scheme, minus gradient of C. Of course, you have to understand, right now whenever I am resolving, this is only representing, what is this? This is a vector equation. This is a vector equation because gradient will be having two components, del by del x I plus del by j here. So I am now dealing with, this is my x component and this is y component. So specifically, first I am only dealing with the terms which are having x component. Okay. So x component will be p of I plus 1 comma j minus Pij by delta x, and for del c by del x, it will be ci plus 1 comma j minus Cij divided by delta x, and sigma k naught is a constant. Is this point clear? Likewise, whenever I will be discretizing it for the situation of j, then I can write it Pij plus 1 minus Pij by delta y, and like this. Is this point clear? Now, I can simultaneously add both these equations to actually calculate the value of Pi and j. From here I will be getting the value of Pi and j. After that, what I can do, I can consider that my cell Ij is lying within the fluid particle, and the other cell, which is I plus 1 comma j and I comma j plus 1, if these are lying outside the fluid domain. So outside everywhere pressure will be, say, P2. In fluid 2 pressure is P2. And if I consider that fluid particle is having volume fraction value equal to C, and the outside cell is having volume fraction value equal to 0. So fluid particle I am considering as my primary phase, and outside phase I will be considering as secondary phase. So everywhere outside value of volume fraction will be 0, but the cell Ij, which is containing that particular fluid particle, it will be having volume fraction either equal to 1 if say it is entirely filled by that cell, or if it is if say I say that inside this cell, this is how my fluid particle is present, then I will be having some non-integral, fractional value of volume fraction between 0 and 1. Is this point clear? So ultimately you will be finding from here that Pij, if Pij will be true for all cells containing, it may happen that I have multiple cells containing the fluid particle. Okay, so Pij is referring to all cells containing what? Fluid particle. Okay, all cells containing fluid particle. So if you try to calculate pressure using this equation for all cells containing fluid particle by combining these two and making C equal to 0 for all the cells other than Ij, which are not containing fluid particle, you will be simply, and considering that the cells which are not containing fluid particle, everywhere outside pressure is P2. Okay, so you will be finding equation Pij equal to P2 minus sigma K naught into Cij. Okay, all are clear with this point. Now you can see this equation is identical to the Laplace pressure equation which we study for drops and bubbles. What is Laplace pressure equation? Inside pressure minus outside pressure is equal to sigma into K naught, where K naught is mean principal curvature, and for spherical shape mean principal curvature is 2 by R naught. So it is 2 sigma by R naught. So simple Laplace equation we are actually now trying to solve numerically. All are clear with this point? So using this equation, you can see by simplifying this situation, I need not to do anything for implementing it numerically. You can easily numerically implement this particular scheme. How? What you can do? You can consider that, say your grid is containing, you have very fine grid, and this grid is containing this much. So everywhere the cells which are filled with completely filled with droplet, you will be giving volume fraction equal to 1, and outside you will be considering 0. And then after that, what you can do, for all the cells which are partly containing the interface, depending upon your approximate geometric analysis, you can calculate the rough approximate values of C. Once you have calculated rough approximate values of C for all the boundary cells, and then what you can do, you can solve this equation for entire grid network, and you can calculate the value of pressure at each and every point. All are clear with this? And then you can plot the pressure data. So it means this simple formulation for the simple situation, whatever I explained, this you can even try by your own. So in order to test the validity of the surface tension methods, I will explain you one of the result in the subsequent slide where this method is implemented and this pressure is calculated, but you can try this by your own as well, because it is very easy to implement. This is one equation, simple explicit equation, which you need to calculate for all the cells Ij which you have contained inside your structure. Is this one clear? All are clear with this idea? Okay, now after making this simplification, we were able to avoid the estimation of numerical estimation of curvature. But whenever in reality we will go, then we will be having complex interfaces where the value of curvature will not be so simple like 2 by R naught. So in all these scenarios, what we need to do, we need to employ the color function data even to numerically compute the value of KH. So how we do that, let's try to see. Okay, so now this is my equation, and in this equation, gradient of H and H and gradient of HC is there. What is this gradient of H and H? Please tell me. Gradient of H and H. This is, yes, kappa. Okay. So mean curvature, I have already told you, it can be written in terms of divergence of the normal vector. Okay. Now, normal vector we already know it can be written in terms of minus of gradient of indicator function divided by magnitude of gradient of indicator function. Okay. In multi-phase flow situations, sometimes density can also be considered as a marker function. How? Let me explain you. So above the interface density of fluid will be 1, and after interface value of density will be 2. and typically the mixture density can be written in terms of rho 1 into h1 plus rho 2 into 1 minus h. Okay. If I take rho 2 common, I can write this equation as rho 2 minus of rho 2 minus rho 1 into h. And this rho 2 minus rho 1 I am writing as rho of s, where s is referring to the difference between phase 2 and phase 1. Now using this equation, if I now take the gradient of this equation, I will be getting on left hand side gradient of rho. Is this point clear? And in the right hand side I will be getting minus rho s, which is a density difference, that will be a fixed quantity, constant quantity, minus rho s into this gradient operator will be applicable on the height function, and gradient of rho 2 will be simply becoming equal to 0 because rho 2 is a fixed density value for a particular fluid. Okay, so from here you can see that even gradient of height function can also be written in terms of gradient of density divided by minus of rho 2 minus rho 1. So this is another way where density can serve the purpose of height function. So sometimes it may so happen that if it is becoming difficult for the numerical solver to calculate the value of height function or marker function, then density in any way we have to use for solving the momentum equation. Okay, so density data will always be with us. So the data of density can also be used as a marker function for calculation of the surface tension force. Okay, so this way then gradient of h will be actually replaced with this, and I will be getting value of surface tension force, something like this. But let's not go into this detail. Ultimately now our aim is to calculate the value of divergence of normal vector, and this divergence we need to calculate with the help of what? With the help of what? The only parameter which we have available for specifying the interface is color function. So this we need to calculate with the help of color function. So let's see how to do this. Okay, so we know that NH is unit normal vector. Okay, but actual normal vector is nothing but our M. So NH is M divided by magnitude of M, where M represents the actually direction normal to the interface. And if you recall the previous lectures, then M I have calculated for reconstruction of the Plick lines. All of you are clear with this? So now it means if I have to calculate normal to interface, first I need to calculate the value of normal vector M. All are clear with this point? So normal vector M will be having two components for a 2D system, Mx and M. Okay, so how to calculate Mx at point I plus 1 by 2 comma j. So if this is my grid, having j plus 1, j minus 1, I minus 1, I minus 2 and I plus 1. So I am trying to calculate the value at point I plus 1 by 2 comma j. All are clear with this point? So at I plus 1 by 2 comma j, this is the midpoint between the two nodes. So at midpoint between the two nodes, I can simply apply the central difference scheme. So that is how I have calculated C at I plus 1 minus I plus 1 comma j minus Cij by delta x. Can you tell me why I have written this? Please tell me why I have written this. Because if you recall from the previous discussion, M vector, which is Mxi plus Myj, was nothing but equal to del C by del xi plus del C by del yj. All are clear with this point? This we have done in interface reconstruction. So that's why Mx, which is nothing but simply del c by del x. And del c by del x using the central difference scheme can be written as, sorry, this was minus del c by del x and del c by del y. So minus of del c by del x will be c at I plus 1 comma j minus cij by delta x. Likewise, can you calculate the value of my at phase I plus I comma j plus 1 by 2? So it will be I comma j plus 1 minus cij by delta y. So I have calculated at these 2 points. Then what left? I have 2 more points. One will be in the left face of this cell and other will be in the bottom face of this cell. So the cell ij where I need to calculate, I have calculated the value of gradient of color function at all its edges. Okay, at all its edges. So if I know the value at all the edges and considering that delta x is equal to delta y, I can simply say that my value at x I comma j plus 1 by 2 will be nothing but mean of all these slopes. Is this one clear? So this is nothing but average of all the slope values. Now I know that the unit normal vector is nothing but m vector divided by magnitude of the m vector. M is a normal vector and n is a unit normal vector along the direction of m. Okay. So n will be becoming m divided by magnitude of m. Likewise, this m vector I calculated at all my neighboring points and this is how I have calculated the value of normal vector. Now one important point, when you have got the value of normal vector, it may so happen that whenever you are numerically implementing, because n vector is equal to m divided by magnitude of m, it may so happen that in some of the cells where m is not valid, for example, if some cell is there which is containing no color function, there what will be value of m? It will be 0. Okay. So for all these cells, it may so happen that magnitude of 0 in the denominator will be becoming actually undefined quantity. Okay. And while numerical solver is doing the computation, your code will be crashing because of this, because computer will not be able to understand what is this quantity and it will be giving a error of NaN. NaN means not a number. Okay. So to avoid this difficulty in the numerical computations, what is done basically, one epsilon, which is a very small value, maybe of the order of 10 to the power minus 6 or 10 to the power minus 8, is added so that your computer, while during the computer implementation, if any error is coming in estimation of normal because of this, that can be bypassed. Is this point clear? So typically you have to understand this point. Whenever you write the computer codes, then at many points we have to take care of all these small issues, and accordingly we need to do certain mathematical modifications to avoid such issues. Okay. After this, Kij, what will be Kij? Kij will be gradient of normal vector. So now if I know the normal vector at all my corners, then I can use the gradient to calculate at the center. Okay. So gradient will be nx at I plus 1 by 2 comma j minus nx at I minus 1 by 2 comma j divided by delta x. Because ultimately, if I am trying to calculate surface tension at ij, the point is center of the node, then curvature also I must calculate with reference to point ij. So whenever I will be calculating curvature with reference to point ij, I can write it as del n by del x with the minus sign, del n by del x plus del n by del y. So when you will be calculating del n by del x at point ij, it will be the rightward face minus leftward, that is n at I plus 1 comma j minus n x at I minus 1 comma j, and the distance between these 2 points is delta x. Likewise, I will be doing for delta y. Once you have the value of k, gradient of c already you know, you can merge all these equations and you can calculate the value of force at different boundary faces of the cell. All are clear with this point? So what I will be doing now, Kij I know, and gradient of Hc already I know. I will be merging these equations and finally I will be getting the surface tension equations for my cells which are under consideration. Is this point clear? So this way of implementing the surface tension force, where we are taking the help of color function to calculate the surface tension, is what we call as continuous surface force method. Okay. Now another way is continuous surface stress method. So maybe because of the interest of time, I will skip this method. But what typically we do in this method, instead of writing surface tension force sigma into curvature, we write surface tension force in terms of gradient of the surface tension tensor. Okay, so surface tension tensor will be actually the representation of the force in terms of tensor notation. Is this point clear? And this tensor notation, then again the data we take help of color function only, and we try to calculate this tensor at different points, and using the data of this tensor then we calculate the value of force. Okay, so this type of method is called as continuous stress method. Okay. But majorly if you go with the majority of the solvers, you will be finding continuous surface force method is actually more popularly used. Even in ANSYS Fluent also you can check, whenever you go for the selection of the volume of fluid method, then below there is one component CSF, one checkbox comes there also. Okay, so another issue is that whenever we do work with the continuous surface force method or continuous surface stress methods, sometimes these lead to unphysical results which are called as spurious currents. Okay, so first let's understand what are spurious currents and unphysical results. So this is the representation of the case which I have shown you, in the previous slide, where what I told you that I have a spherical body and this spherical fluid particle is completely at rest. Okay, and I need to calculate the pressure distribution across this particle because of the surface tension force. So here you can see that this represents the contour of the pressure. So in this contour you can see this is say y-axis, which is my y-axis, and this is x-axis, so this is x-axis. This is the y-axis, and along the z side we are showing the magnitude of the pressure. So first point is very clear to us that if I have this spherical system, then if I plot the data of the pressure, then outside everywhere pressure will be low. Within the droplet or the bubble I will be having high pressure, and again pressure will be low. So I should get this type of profile. Is this one clear? And whenever I will be representing this on a three-dimensional plot, then this profile of the pressure will be appearing like a cylinder. All are clear with this point? Anyone is having any doubt? Because pressure inside pressure is high and outside pressure is low, so it will be appearing like a cylinder. But whenever numerically we are calculating the pressure, instead of getting a smooth curve, what we do get, of course, in the center we have some high pressure which is almost uniform. Outside also pressure is fixed, almost uniform, but near the interfacial boundaries, pressure instead of sharply rising, it rises gradually. And of course, the thickness of this gradual rise can be controlled by decreasing the cell size. If I take more number of cells, then the thickness of this gradual rise can be decreased. Is this point clear? But other issue with this is, near the interface, whenever you are plotting the pressure, you are finding that the variation of pressure is not smooth, but it is having some peaks and valleys. So rather than getting a smooth pressure field, what we are getting? We are getting the oscillatory pressure field. And this oscillatory field is mainly existing near the interface. Is this point clear? Now, corresponding to this pressure, if you see the velocity field, if in my formulation itself I assumed that everything is stationary, then the actual magnitude of the velocity field at each and every point across this would have been 0. But mostly we see in majority of the region pressure is 0, but velocity is 0, but particularly near the interface, where we are observing this oscillatory pressure field, corresponding to that we are having some localized motions in the localized velocity field. And this velocity, based on the actual definition of the system which have taken, is actually unphysical. Is this point clear? Because if in my mathematical formulation I assumed that it is completely stationary and then also I am getting certain oscillations, it means all these velocity oscillations are actually unphysical. All are clear with this point? So if these are unphysical velocities, typically these are called as spurious currents. Okay, so it means that whatever the method I explained you, you can see over here, different Laplace numbers are used, different liquid to gas density ratio is used, viscosity ratio is used, and d by h is the ratio of diameter of this particle to the cell size. Okay, so in certain cases cell size is considered majorly in the range of 30 to 32. So it means along the diameter how many number of cells I am having? I am having either 30 or 32 number of cells in my grid. So in this scenario you can see that if you use CSS method, then this capillary number is calculated. So capillary number is nothing but U. What is the definition of capillary number? U mu into V by sigma. Okay, where sigma is surface tension, V is velocity. So if you calculate capillary number, then maximum capillary number you are obtaining in the range of, for CSS method, CSF method and front tracking method. Okay, so this is the range of capillary number we are getting. That means we are getting small amount of velocity. In certain cases it is written disintegrates or blows up. What is the meaning of this? If in your numerical solver the magnitude of spurious currents becomes significantly large, then what will be happening? These spurious currents may break the interface. All are clear with this point? Because ultimately spurious currents are nothing but some random velocity fields. So if the magnitude of these random velocity fields increases significantly high, then these can even lead to breakup of the interfaces. And these breakups of the interfaces will be actually unphysical, because as per physical conditions these does not work. Okay, so that is what is specified over here. Now this particular case is called as actually static case for test of the surface tension methods. Along with this static, we can also have one test which is called as dynamic case. Okay, so in dynamic case we can consider a bubble or drop which can either rise or fall. So if I have a rising bubble, then of course there will be some deformation in its shape while it is rising, and if I have a falling drop, that will also be having certain shape changes. And other than that, this is one of the dynamic case, but one more advanced version of dynamic case could be that while this drop or bubble is rising upward or falling downward, then along with that it is also having some surface oscillations. Okay, So it is also having some surface oscillations, because of which it is compacting, expanding, or even some capillary waves which are actually traveling on the surface of this. So that could be the more advanced case. So here again this spherical case is taken where deformation of the shape is taking place along with the surface oscillations. So here you can see the value of velocity field majorly, because in this case bubble or drop is moving, so there will be some physical velocities, and you can see the order of velocity is perfectly fine. So because of the motion, the actual velocity field, the physical velocity field is sufficient enough that it is suppressing all the unphysical velocity field, and corresponding to that you are getting your good smoothened pressure profile. Okay, and these are the amplitude of oscillations which are taking place with this, and these are estimated from theory as well as from the simulation on a 64 by 64 grid, and ultimately you are able to find there is a good accuracy. Okay, but one important point, you can see that when we are comparing the methods, we are writing WOF CSS, WOF CSS K8, and then PROST PCMM and height function. So typically the first two are used with interface reconstruction methods. These two are used with front tracking methods, and height function based surface tension force estimation is a new method which typically is being employed with interface based reconstruction techniques, and this method has a good amount of accuracy in comparison to all other methods. Okay, so is this point clear? So height function is a recent development, maybe 10 years or 15 years old, where the estimation of surface tension force using this method is actually giving good amount of accuracy in comparison to all the other previous methods. Is this point clear? Now one important point you can observe that when I am writing WOF CSF, then one K8 is also written over here. So what is the meaning of this K8? So meaning of K8 you can understand from here. Typically whenever we apply the continuous surface force model, it is the method which is having high chances of occurrence of the spurious current. Okay, to avoid these spurious currents, what is typically done, the volume fraction field is first smoothened near the interface, and after smoothing of the volume fraction field with averaged out volume fraction field, all the parameters are calculated for the estimation of the surface tension force. So this is called as smoothing. So smoothing can be done in two ways. One of the simple way of smoothing is this averaging equation. So you apply this equation of C tilde ij, which is half of Cij plus 1 by 8 of Cij in all the neighboring cells, and once you established the new data of C tilde ij, then use C tilde ij for calculation of curvature, and then it used for the surface tension force. Another way is, near the cells, boundary cells, you define some zone, and in this zone you define some smoothing kernel function. So we can define one smoothing kernel function. So here you can see when the h tilde height function is calculated, it is hx multiplied by some smoothing function where epsilon represent the radius of the smoothing zone, which is considered for estimation of kernel function. And now then distance of the point of interest with other points which are residing inside this circle is estimated, and using this data we do calculate the value of the C tilde, and that finally is used to calculate the value of curvature and the surface tension force. Okay, so if we apply this smoothing, then our whatever is our that initial method is continuous surface force method. So if we first do calculate the value of averaged out or smoothened color function, this smoothened color function can be employed for estimation of mean curvature of the interface, and then surface tension can be calculated. This type of method will be giving better accuracy, and it will be avoiding the presence of spurious currents. Is this point clear? So maybe with this we will be closing our discussion on estimation of surface tension.